Back, everyone. So last but not least, we have another talk on learning this time. And Nikito is going to tell us about universal extrapolation and its connections to Kolmogorov complexity, of course.
Thank you. So I'm sorry for that. This is not about MCSE. Okay. And this talk is.
I'm leaving right now.
And this talk is based on joint work with Shuichi, but actual contributors Russell and Levy, I think. So okay. And first of all, one of the important questions in this workshop seems to be to clarify the relationships between learning and meta complexity. And we want to establish some theory. And to establish theory, maybe we need some samples. And the goal of this talk is to provide one example of one direction from learning to meta complexity. And there are many novel techniques to show this direction. And I think universal extrapolation is one candidate for this direction. So the goal is to explain this idea to see the relationship between learning and meta complexity. Okay, first of all, let's begin with some history. And so this idea was originally introduced in the context of learning theory in Pestan, namely to show the implication from the non-existence of one-way function to learning. And okay, this fascinating. So this is a very fascinating direction because if we can establish this direction, we can guarantee either theoretically guaranteed cryptography or theoretically guaranteed learning. So this is very win-win situation. This is very positive implication. And this fascinating direction was first studied by Impagriat and Levy in this paper. And in this work, they proposed a very high-level ideas of universal extrapolation. And unfortunate thing is, actually, so at least I did not find any formal statement in the sense that which kind of learning tasks can be done based on their idea. Yeah, so
there's a story about that.
Yeah.
But maybe later.
And actually, I have spent almost all the time with my PhD.
Nina did not, at the time, did not like the word learning and did not think it described, but I said that at his birthday party over the summer, and he said he's changed his mind about it.
Wow.
So it's now okay.
Okay, now I can use
now it's a bit of journal version final.
Yeah, exactly.
And fortunately, so there are many follow-up works that study in formal way. So which kind of learning can be done in PESA, like as average case pack learning and learning adaptively changing distribution. And they use a very sophisticated and somewhat seemingly related idea of this universal extrapolation, but it seems a bit different from the original idea. And recently, so I and Hirahara revisited the idea of universal extrapolation, and we noticed that, oh, this is really amazing idea. And actually, by revisiting this idea, so this very first idea in this context actually can show these follow-up work. Actually, it simplifies and improves the previous randomity result. So I would like to explain the idea. And let's begin with the what I call impersonation. This is actually learning adaptively changing the distribution. Okay, now so you have your type for learning. And this can be maybe a person or the computer, maybe some mechanism in nature, I'm not sure. But okay, let's assume that your target is described by some secret S. And this target outputs some message sequentially. So let's say X1, X2, X3, and so on. But so this target may use some internal random, so random coins. Namely, so this randomness determines the distribution of each message. And in general, this can be correlated with each other. And okay, now your task is, okay, you do not have any explicit description of this, your target at present. So at the first time, but you can observe these outcomes of your target. And the goal is to, at some point, you say something, okay, let's say at ith step, instead of your target. And the goal is to simulate the distribution in the sense that so you can win in this game if your distribution of this xi is statistically close to the ith distribution, given the previous observation. This is the goal. And this impersonation game actually captures many natural learning problems. So let's say, first, let's consider distributional learning. So in distributional learning, so you have Oracle access to some unknown distribution. And let's assume that so this distribution is sampled by some secret S-size target. And for each axis, you can get IID sample. And the task is to output some description of distribution such that the total variation distance is small. And immediately we can notice that so this can be formulated as a previous impersonation game. So in this case, the secret is just the target distribution. And for each round, by using internal randomness, your target samples the new sample. And at some point, if you can simulate the distribution, then this should be your hypothesis, approximate distribution. And we can also capture agnostic learning and P/polysamplable joint distribution as an impersonation game in some way. So where we consider setting that so this distribution is again samplable by some S-size circuit. And for each axis, this distribution returns a pair of example and binary labels. And the goal is to output the hypothesis such that the error probability according to this distribution is not much worse than the best possible predictor. And in the standard setting, when we consider agnostic learning, we often restrict the concept class. Like we consider best predictor in some restricted concept class. But for now, we consider all functions. Namely, the task is to simulate, so estimate statistically optimal predictor. And this can be also regarded as a kind of impersonation game where your target interchangeably so says X and label and X and label and X and label. And so at some point, given some X, if you can simulate the distribution of label, then now you have distribution. So by sampling many experiments, you can find which label tends to be occur in the next round. And this year the statistics. So this approximate statistically optimal predictor. Okay, now we see the motivation to study impersonation game. And my friend is okay. By using this universal extrapolation idea, we can solve this problem. And so this gives us the idea of solving impersonation game. Okay, the idea is following. Okay, now you do not know what is your target, explicit description of your distribution. But okay, let's extrapolate next thing as if your target is the time-bounded universal distribution. Now I define some notations. So in this talk, I fix some universal Turing mass in U, and let's define t-time-bounded universal distribution, Qt as a distribution of the outcome of universal distribution, executed only in t steps for random input. And I introduce the notation next k of x and Qt as a distribution of next k is following the given prefix string under the time-bounded universal distribution. Now the proposal is 4. So this is your target described by each secret. And you can observe x1, x2, x3, and so on. And and for simplicity, let's assume that we know that the length of each block is k. And for extrapolating ith step, the proposal is following. So you just extrapolate the string according to this distribution next to k of the previous observation under universal distribution. And the claim is the following. If the total number of rounds is sufficiently larger than the amount of seed, then this idea works well for almost all blocks. This is more quantitatively, so we can show the following. Okay, let's say this phi is unknown your target program of size S, and R is a random seed. And let's call each distribution of each block as a x1, x2, and xn. So total number of rounds is just n. And let's assume that each length is exactly k. Then, if the time bound for the universal distribution is sufficiently larger than the running time of your target program, and if the total round is sufficiently larger than this quantity, but in this order, then the total variation between your target distribution, the distribution of xi given the previous observation, and the distribution next block under the universal distribution is at the most epsilon. Epsilon can be very small, or very small, with a high probability over the choice of position and past observation. And we will see the proof later. Actually, this can be shown very elemental. But before that, I would like to mention something remarks. First, since this is a beta complexity workshop, maybe we should discuss about the relationship to beta complexity. And I'm not sure this is the best explanation, and I would like to ask you as a specialist in beta complexity, to be honest. But okay, I have 2 minutes. So so interpretation is like this. So actually, let's look at the information content of string and the universal distribution. And this is almost equivalent to so-called probabilistic Kolmogorov complexity. This is a probabilistic variant of Kolmogorov complexity. And okay, roughly speaking, this is a Kolmogorov complexity under the presence of common random reference. And we can show that actually this quantity is almost equivalent to pk. So namely, extrapolating under a time-bounded universal distribution is essentially the same as a betting strategy, where your belief is like that. So you believe some string y follows x with this certain proportional to this 2 to the minus pk polygon. And this can be seen like as a kind of Occam Fraser phrase, you know. So you believe okay, some hypothesis y for x. If the hypothesis is succinct, you put more weight on proposal to this. And actually, this is a proposal in Solomon inductive inference. And in the original work, he uses the time-bounded setting. But in this setting, we use PK point. And so I want to quote the sentence from Imperfect Reving paper. So we implement Solomon recursion theoretic notion of extrapolation complexity distributed setting. This idea. And in my opinion, so namely, okay, extrapolation, universal extrapolation in this formation do a kind of a bit complicated thing than the standard meta complexity problem. Because in the standard meta complexity problem, the task is for a certain hypothesis, calculate certainty in this betting strategy. But to extrapolate under universal distribution, we need to sample according to this value, to the minus pk point or something like that. So in general, this can be much harder than just computing some specific. Okay. Okay. Just computing specific complexity. So namely, we should discuss now the complexity of universal extrapolation. And to construct some learning algorithm, what we all need is, so we do not need the complete simulation with universal distribution, and just so we can allow very small statistical error. So let's say, so this UV machine is so for given prefix and parameters, and actually this is the accuracy parameter, try to sample some string according to the type distribution, universal distribution, within some statistical distance, more statistical distance. This is sufficient to construct the learning algorithms. And the question is, what is the computational E? And so I can show that, so we can show that actually this, okay, if there is no one-way function, more precisely infinity of one-way function, then we can construct a universal extrapolation machine that works in worst case sense of prefix x in time polynomial in the length of string and parameters and to do the computation. Where, so for simplicity in this work, we define computation text by using information point and universal distribution. And actually, this complexity characterizes the existence of one-way functions, the context also. And I will not prove this lemma, but at least I will show how this UE machine looks like. And so, okay, intuitively, this is based on distributional invariant. Let's say some string is sampled according to universal distribution, and so we only know a prefix, and the goal is to extrapolate. And since this universal distribution is sampled just by executing universal Turing machine, we know the sampler of this distribution. And by restricting our attention to the prefix part, we can get the corresponding sampler to the prefix part. Then we first invert this prefix part, more precisely distributional invert this prefix, and we can get a uniform sampler, almost uniform sampler from the consistent system. And once we can get the C, by calculating, recalculating by using the whole sampler, we can extrapolate something so that the prefix should be consistent prefix text. And actually, this is our UV machine. And as a consequence, we can show several learnability results in Hessian, namely under the non-existence of one-way function. So in Hessian, we can win the impersonation game in polynomial time if the computational depth of the secret of your target is logarithmic. And for instance, if your secret is selected according to some samplable distribution, then with high probability, this is the computational depth is logarithmic, so we can win in polynomial time. Namely, so in Hessian, we can solve, for instance, distribution learning and agnostic learning as long as the secret distribution D is sampled according to another samplable distribution. But I want to emphasize that, okay, this is a bit confusing. So let's consider distribution learning. And this learning is different from learning a distribution over the choice of G and D. So this is different. So the difference is, so in this formulation, your target is D. So you consider the conditional distribution under the event that this generator selects, and this is different from a distribution over G. And in the latter task, so this task is much easier than the above one because there is no non-uniform secret here, and so we only need very few samples. Of course, we can solve this, but this task is much easier, so the above task is much harder. Okay, now let's go back to my technical part. So we want to see the proof of this technical method. And actually, the proof is based on two very fundamental things: domination property and the chain rule for K diagrams. And so let's begin with reviewing the notion of K divergence. So let's say you have two distributions D and E, and the K divergence from D to E is defined as this. So X is sampled from distribution D, and we consider this quantity expectation. And we can also define, extend this definition to conditional distribution. So conditional on D and E, and this is actually the same, except that we consider conditional distribution instead of the whole probability. And this K divergence somehow measures the closeness between the distribution D and E. But okay, one very famous interpretation is like this. So let's rewrite this part like this by using the logarithm. Then, so first we take some sample from the distribution D, and let's consider the compression of this story. And in statistical theory, so that optimal coding length in expectation is this length minus log of the probability that D produces some sort of X. And if you know what is your distribution D exactly, then you can accomplish this optimal code in statistical theory. But okay, let's assume that you do not know, we do not know what is the distribution D, and instead, let's use some distribution, another distribution. And intuitively speaking, if this distribution E is very close to distribution D, then the loss of coding length should be. But if this E is much different from distribution D, then the loss of coding should be very large. And actually, this K divergence measures this loss of coding length in expectation. So this part is coding length according to distribution E, and this minus, so we subtract optimal coding part. So this is the lost part, and we take expectation. And this situation is very similar as like our impersonation. So in impersonation, then we have sample from unknown target distribution, IR. And we do not know what is IR. Instead, we manage with some time-bounded universal distribution. So the question is how close this distribution, particularly what is the K divergence between these two distributions. And first claim is, so if we consider this K divergence, and if we take the time band sufficiently larger than the running time of this program, then the K divergence is at the most the program size. And this order, so the hidden constant depends on the encoding. This follows from domination, which states that so for every string in support of your target distribution, this holds. So the probability that X comes from the time-bounded distribution is at least this quantity. This holds because with this probability, the prefix of randomly selected program coincide with the description of your target. And under the event, the conditional distribution of this should be equivalent to your target distribution. And by taking logarithm and arranging this inequality, we can get this inequality. The coding length according to universal distribution is at the most the optimal coding length plus the length of the probe. And by taking expectation, we have this inequality. And now we have the bound for whole K divergence. And intuitively speaking, if we have n blocks in total, and if the total K bound is the size of program, in expectation, the K divergence in each block is at the most this value divided by the total round. And we can verify this by using chain rule of the K divergence. So let's rename the distribution, this distribution. So let's say X is your target distribution, just Q is the time-bounded distribution. And let's separate this distribution into groups. And let's say, so the length of each block is the same. Then we can rewrite these things like this. And so, personally speaking, we use the information inequality to truncate this part. We can rewrite this place like this. Then we use the famous chain rule for K divergence. which states that so we can separate the whole K divergence into the sum of K divergence for conditional distribution of isostate given the previous blocks. Then dividing by n, we can show this inequality. Or in average setting, so over the choice of rounds, we can bound the K divergence at most this quantity. And if m is sufficiently larger than this quantity, we can bound this. Now I almost finished the proof. So now we have this inequality, and by using Markov's inequality and non-negativity of K, so this is a very standard discussion about probability theory. So we can show, so with this probability, high probability over the choice of points and prefix string, the conditional version of K is at most this function. And let's see this part. So this part is exactly the next block probability under universal distribution. So given the previous block produces x at most I minus 1, and we consider conditional distribution. This is exactly next. Now to transform K bound to total variation distance, we use Pinsker. And we can get this bound. And in this sense, therefore, we can verify the correctness of this idea universal extrapolation by using very fundamental domination property and chain rule like this. Okay, in conclusion, so I explained the idea of universal extrapolation. So let's say extrapolation and universal distribution. And this terms in the inbound solution again is very small accuracy if the round is sufficiently larger than the amount of sequence. And the proof is very fundamental. This and it shows that so it implies the running this like the exponential running in computation vector. And one open, so I would like to share one open question. And so the question is, what is the complexity of worst case setting of universal extrapolation, particularly polynomial time universal extrapolation for every purpose? And actually, to construct, for instance, natural distributional runner or agnostic runner, we can allow some statistical K error, like as a computational depth of the prefix string X. And but I do not know any interesting about to show this other than P is solvable in worst cases. And the point is in heuristica, under the average case easiness of NP, we can solve the computing of this error. So computing of time-bounded Kolmogorov complexity within this error can be solved in heuristica. But we do not know at present how to sample from this measure. So this can be an interesting question. Okay, that's all.
Can you use like a spiritual information?
Sorry, can you?
Because in heuristica we know spiritual information follows.
Yeah. But
so spiritual information, like if you want to sample a string y, right, in the same sense, you just need to, given the prefix x, right, then you just need to pay component x comma y minus like component of x.
Yeah.
This is like
yeah, we can use the symmetry function, but it does not specify how to sample according to.
like if the spiritual information hold, can you just pick random programs?
Random program and why?
Because it says like if spiritual information holds, it's saying like given x, right, and to find y, you just need to pay for like basically the conditional Kolmogorov complexity is the total Kolmogorov complexity minus k of x, right, and then you sample each. So it's kind of so you kind of sample every string proportional to
Oh, okay, this, it's just,
Oh, yeah, maybe.
like kind of impromptu softball, maybe.
Okay, I'm not so sure, but it will very well. Actually, I have considered this, but previously I could not so like the distribution run with, I forgot the reason. So,
Yeah, maybe.
Other questions?
This pattern matching, the dependence you had was probably one minus delta, and the bound was like inverse linear delta.
yes, but for map learning, just we start to take the constant and use the logarithm numbers and to test with
So what, sorry, what did you say about getting like a logarithmic dependence on delta? You don't think?
So in the case of running, in the case of agnostic running, we can reduce the dependence of delta like as a log of delta inverse.
Okay.
Unless anymore. Oh, yeah, Mark.
Where would be the right place to put a complexity restriction on, the target concept? I know that right now, your target concept is a hidden program that takes a random seed and then generates blocks, right? And it's a general Turing machine. It has a time bound, but nothing else. Suppose I wanted to learn like a parallel machine, like NC or something, does, is that, is there a different universal distribution for?
Maybe we should define universal distribution by using the NC universal.
Okay, so you would redefine the universal
Yeah, yeah.
distribution to use the universal machine that's appropriate for your target concepts. Would you expect anything weird to break if you do that, or?
I am not sure, maybe someone is perhaps.
When you, okay, so we need to like do the distributional sampling of, distributional reversion of the one-way function in order to, I mean, you said that you're doing this process by like looking at the conditional distributions, but you have to actually like invert the whole process in order to sample from that conditional distribution. In order to do that, even if the concept you're learning is in a small complexity class, you have to be able to find random preimages. The way we did that is to look at one-way functions that combine the output with like the values of random hash function. So you'd have to have a class that can handle random hash functions. That's probably not so bad because you can do that in like AC0 mod 2. So you might be able to do something like for a class that contains at least like is stronger than AC0 mod 2. I'm just trying to like, I think that's the only thing we actually use is like concatenation with hash functions, right? To do that inversion.